This is Dr. Clark, and in this video we're going to learn about triple integrals, what they are, and why they're important. Let's get started. So the main idea for triple integrals is going to start with volume. And when you have a triple integral, it's going to look like this, with three integrals, one for each dimension for a three-dimensional solid. D represents the region, some three-dimensional region D, and then you have a function that you're integrating, and then dv would be that volume element. So of course in one dimension we called it dx. In two dimensions we had dA, which was a small patch of area multiplied by the function. Well, now we're in three dimensions, so we have a small patch of volume. We take that volume times a function, and that gives us a quantity. If the function's 1, then we just end up adding up the volume. So this triple sum is going to sum up all those volumes, and you'll just get the volume of the region. So that's the sort of the natural application. Of course, the question is, how do you compute this? And that's going to be using Fubini's theorem. So Fubini's theorem takes this region D right here and turns it into an iterated integral with actual bounds. Now, of course, this is going to be the hard part, is figuring out for a given volume, how do you make the bounds actually describe that region? In rectangular coordinates, dv, the small patch of volume, gets written as dz dy dx. Of course, a small, little square of volume, dz dy dx, or a cube rather, a small rectangular prism of volume. Okay, in this case, what we're saying is we can describe the region algebraically saying the x's always go between a and b. For a given x, the y's go between g and h. And for a given x and y, the z's go between capital G and capital H. So G and H capital are sort of the top and the bottom of this volume. Little g and little h are sort of the left and right sides of that function, and then a and b are sort of the x's where it starts and where it stops. So the real trick is, can you take a region and turn it into an algebraic description, which can be your integrands, and then the volume element is just dz dy dx. And when you do the integral, you'll integrate the z's first, you'll end up with x's and y's left over, then you'll integrate the y's, you'll end up with x's left over, then you integrate the x's, and because x goes from a to b, you'll end up with a number at the end, which in this case would be a volume. You can do the exact same thing for mass. We learned before in two dimensions, if you have a density times dA, well, now we just have density times dV. So if rho represents the density of an object per unit volume, multiply by volume, that gives you a mass. Add up all those masses, you get the total mass of some object. And of course, this is just thinking physically. This mass could be a probability mass, and then you'd compute probabilities, or it could be just any function that you want, and when you integrate it, you'd get the sum of that function over the region. And you can, so any function you want, and this is sort of the utility, the versatility of the calculus, and we'll be able to do this for essentially any function you want, as long as we can describe the region this way. Now, for convenience, some regions maybe you don't want to do zyx, maybe you want to do some other order, depending on how the volume is written down, and we'll see that later in some examples. Okay. Now, if you wanted to know center of mass, we're just going to take the same equations we had before in two dimensions and upgrade them to three dimensions. They're going to look like this. So your x moment here is taking the density times the volume element multiplied by x. That gives you sort of a distance away from the yz plane. So we call that the moment in the yz plane, because x is the distance of a point away from the yz plane. Similarly, y is the distance away from the xz plane, z is the distance away from the xy plane. And so when you do the distance times this mass thing, add them up, that gives you a moment. Add up all the moments, you get a total moment. Divide that by the mass, you'll get the center of mass in x, y, z. And of course, if you need the mass, you just integrate the density function on the region. So that's sort of a standard application of triple integrals is center of mass and mass of an object, but really any other functions could work as well. All right, that should give you the main ideas of triple integrals, and then in the next video we'll see how to do some examples.